This is one attempt to do this on a scrolling thing. We'll see how that works. This is one attempt at the 2022 multiple choice 1 to 13 so far. Okay. Which of the following statements about atomic emission spectroscopy is not? Obviously it's in bold, so that's important. Which of these is not correct? Okay, each element has a characteristic spectrum. Well, that is demonstrably true. That is the whole point. Okay, visible light is used to promote electrons to higher energy levels. This is atomic emission spectroscopy, so that is looking at what's produced afterwards, it being falling down, but also atomic emission spectroscopy used heat. Okay, so this is the correct answer. Just to check, the lines arise from electron transitions between one energy level and another. That's true, it's just they're falling. The quantity of the element can be determined by the intensity of the radiation emitted. That's kind of, again, the point. So definitely B. Okay, I can get my mouse to move. Question 2. How many electrons are there in the highest energy subshell of a CR+ ion in its ground state? And then I've pulled the databook page for this one. Okay, so I am looking for, here's my chromium. Okay, I want a chromium plus. This is the sneaky one though, so just be very careful. Okay, so we've got 1s2 filled up, and then we've got 2s2 and 2p6 all nicely filled. We've got 3s2, 3p6, everything's kind of going nicely up until then, and then we've got our kind of slightly strange thing. Okay, so 4s2 is our normal filling here, okay, and then we'd have 1, 2, 3, 4 to get 3d4, but chromium is your weird one, where basically there's a payoff. If it promotes one of the 4s's up into 3d, it can get a half-filled subshell, which is more stable. So this is where it would normally get to, is 4s1 3d5. Now they're asking you for a CR+ ion, so basically I've lost an electron, and then we just go back to our normal filling and losing order, which is that you lose from the highest shell first. That is 4s, so that comes out. So how many have we got in our top energy level is 5. It's quite a lot of work. Okay, question 3. The formula of an octahedral complex ion containing a metal ion M2+ and the bidentate ligand L- is. Now, I will fully admit that I had to look at this quite carefully. You have to be very careful about what you're reading here. So octahedral tells you that you have 6 points connected. That's what octahedral means, because we've got our kind of 4 in the centre and then up and down. Okay, so 1, 2, 3, 4, 5, 6 to get our octahedral. Not the nicest diagram, but okay. It's got a metal ion in the centre, which is M2+. Okay, so this central point here is our M2+, and it tells you it's a bidentate ligand. So that means for me to get 6 points connected with a bidentate ligand, that's one that can connect at 2 points, I must have 3 times the ligand. Okay, now you've got to figure out your actual charge on this. Okay, so I've got 3 times the ligand, so that's 3 times -1, because it tells me the ligand is L-, so that equals -3. Okay, I have 1 times +2, because that's my metal ion, that's +2. Add them up as if I was doing any kind of normal transition metal complex thing, I get -1. So that means my formula is Ml3 negative overall. So D. Again, quite a lot of work on that one. Oh, sorry, scrolling badly. Here we go. Question 4. Which of the following statements about heterogeneous catalysts is, again, we're going with the not correct. Okay, hetero means different. Okay, that's the most important thing we have here. So they are found in the same state as the reactants. No, because they are different. To be very clear about the rest of it, this is just definitions of what happens. They adsorb reactive molecules on their active sites, absolutely. They provide reaction pathways with lower activation energy, absolutely. That's just catalysts in general. They have unpaired d electrons that allow activated complex to form. Basically, our heterogeneous catalysts are generally transition block metals, so there's our deed. Okay. Question 5. A disproportionation, I can't even say that one, a disproportionation reaction is a redox reaction in which an element in a single substance is both oxidized and reduced. Okay, so definition of something which you've never seen, but that's okay. You know what a redox reaction is, and they're saying an element in a single substance, okay, in which the following does a halogen undergo disproportionation. Okay, right, so you've got to look for your halogens for a start, and they have to be in a single substance. So look at the first one, here's chlorine, that's okay, it's in a single substance. And then look at where the chlorine ends up. The chlorine ends up over here with the potassium. So basically we've got Cl2 going to Cl minus. Well, that's just one thing. It's gained electrons, so it's been reduced, and that's it. Okay, and you've got to work through the rest of them and see if you can find out something that's happening in a similar way. So we've got here IO3 minus, so we've got an iodine in here, and we've got iodine as an iodide here, and we end up with iodine as its molecular. But the problem is here, it says it's an element in a single substance being oxidized and reduced, and these are not in a single substance, so that's not okay. Our next one, we're looking for our halogen again. So here's our iodine, and we've got chlorine. The iodine ends up in one place, so only one thing could have happened to it. The chlorine ends up in one place, so only one thing could have happened to it. Okay, if you look at the last one, however, here's my halogen. It ends up in NaCl, and it ends up in NaClO. So we've got two different things that have happened to the chlorine. That's the only one that makes sense. If you do it by elimination, it's probably as easy as trying to actually calculate what's going on inside the NaCl0. Okay. Question 6. Which of the following is true for a neutral solution at 325 K? Okay. Right, so you do have to do a little, I've pulled out the data book page here for the properties of water, because there is something very specific that we have here that is important. The ionic product of water is 1.01 times 10 to the minus 14 at 25 degrees C. Okay, that is 298 K, that's your standard temperature. So basically this can't be true, because we should be aware that what we're looking at here is Kw, which is your dissociation constant of water, and we should know that that changes with temperature. Okay, so what we're getting here cannot be exactly the same as the ionic product that we have at 298 K. Okay, now you have to figure out what's going on with what happens if you increase the temperature. Okay, right, to start with, okay, increased temperature means that we've got an increased dissociation. That's really what's happening. So if you think of your water molecule, what's happening is more of them are dissociating into hydrogen ions and hydroxide ions. Okay, but for every single one of them, for every single water that goes, you get one hydrogen ion, you get one hydroxide ion. So this is always true as long as we've got a neutral solution, i.e. one that is the same number is being moved. Okay, it won't be pH 7, because if you change the dissociation at all, then my hydrogen ion concentration has to change, so it can't be 10 to the minus 7, which is your normal pH. So get rid of that. And D is actually exactly the same as A, so you could actually have got rid of A and D just purely as in we can't have two correct answers. So it's not lovely, but if you're careful, it's an okay question. Okay, question 7. We've got an equilibrium here. We've got our delta H at minus 196, can't read. So we're looking at a exothermic reaction going forward. Which line in the table is correct for the concentration at SO3 at equilibrium? So we're looking at this side, and the equilibrium constant when the pressure of the equilibrium is increased at constant temperature. Okay, so we have, first of all, right, if I increase pressure, that will favour the moles with the least, favour the side with the least moles. So we have on this side, we have 3 moles of gas, and on this side, we have 2 moles of gas. So if I squeeze it, it is going to favour the forward, and if I favour the forward, I'm going to increase the amount of SO3 at equilibrium. Okay, we are at constant temperature. That's the important thing here. Constant temperature means that I am not changing the equilibrium constant. So correct answer is A. Question 8. Oh, I didn't manage to get that centred particularly well, but never mind. Ignore 9 until we get there. The standard enthalpy of formation of sodium chloride is represented by... Okay, this is a straight definition that you need to know. Okay, so we are producing 1 mole of the substance. That's obviously the most important thing. And it must be elements in their standard states that you make it from. Now, if you're not sure of what the standard states are, pull up your data book, go to your melting and boiling points page, and you're looking for what it would be at your 298K. Okay, obviously shift it to 25 because it's in degrees. So we've got our standard enthalpy for sodium chloride. So sodium chloride in its 1 mole of the substance, so it would be made as a solid, okay, not a gas, so we can get rid of A. And 1 mole, so I can't help, that's not helping. Elements in their standard states, right? So sodium ions, that is not a standard state for sodium, so get rid of that one, okay. And sodium is a solid, that's fine. Chlorine is a gas, absolutely, but chlorine in its standard states is Cl2, not Cl, so D. Question 9, we're looking at a rate equation. Okay, so you're expected to just be able to work with these. Right, so we've got rate equals our rate constant, we've got A squared and B. Which of the following statements is correct for this reaction? So if I've got A squared in this one, what I'm saying is if I double A, I quadruple the rate, because that is saying it's second order. Okay, what I'm also saying for my B, okay, this one is if I double B, I'll double my rate because that's first order. Okay, I can also look at that entire equation and I can say that I've got second order and a first order, so overall I've got third order in my equation. Not that you need to know that, but that's just something you should be able to pull. Okay, which of the following is correct? Doubling the concentration of A will double the reaction rate. No, because it will quadruple it. Double the concentration of B will double the reaction rate. Absolutely, that one's right. And just to check, C and D, doubling the concentration of B will have no effect. Well, yes, we've just said it would, so it couldn't be that. Doubling the concentration of A and B will have no effect on the reaction rate. Definitely not. I don't think that's the worst rate equation, one that I've seen. Oh. Question 10. The order of a reaction. Right, so is it A depends on the stoichiometry of the overall equation? It's a sequence of steps in the mechanism, controls the speed of the overall reaction, can only be obtained by experimentation. This is a straight KU thing. It's the whole point about orders of reaction. It is not the stoichiometry. Be really careful about that. So it's not your big numbers in the balance. That's to trip you up, really, to do with equilibrium constants, because that is the stoichiometry. Sequence of steps in the mechanism. It will totally depend on the steps in the mechanism. It'll matter which ones are fast and which ones are slow, but it's not a definition of the order. You have to work that out from the experiments, and controls the speed of the overall reaction. You could argue that will have an impact, but exactly what that's going to be in terms of what the actual rate is, no. Okay, question 11. Which of the following graphs shows the variation in entropy, S, as the substance is heated from below its melting point to above its boiling point? So I'm going from a solid to a liquid to a gas. Okay, solids, I think, like, you know, probably first year when you were looking at solids and saying these are particles that are neatly arranged, they kind of suggle a bit, but they don't do much. So in terms of entropy, very low. Okay, liquid molecules, particles, they kind of move around a little bit, but they're all still connected, and so you've got your conservation of volume. There's definitely more entropy there, but it's not crazy. Gases are mental. Okay, they zip around all over the place, and so what we're expecting is a shift up from solid to liquid and a massive jump up from liquid to gas. Okay, and we're expecting a phase change point. So we're not expecting a gentle curve, we're expecting a sharp shift. Okay, so basically it's not A and it's not B, we're to C and D, and we're looking for the sharp shifts, and there's a solid to liquid and there's a liquid to gas. So correct answer is C. Okay, question 12. Question 12, not the nicest. Okay, which of the following diagrams represents the hybridization of orbitals in a carbon atom of ethine? Okay, so ethine, you should recognize this as ethine. Okay, so what we've got in, if we look at just one of the carbon atoms, so let's just look at this guy here and ignore the other one. Okay, so this has 2 sigma bonds that have been connected. Okay, so that means that we have 2 sigmas, must mean that I have got my S, oh wait a minute, sorry, draw it out here. Okay, here's my 2S and here's my 2P. Okay, so you started off with this bit here, okay, and then you promote out one of them so that you can manage to actually get 4 electrons to play with. Okay, and then we're going to hybridize to get 2 identical ones at my lowest level, so that is going to be an SP hybridization, leaving me with my 2 single P's, which can be used to make my pi bonds, of which again you have 2, one on either side of the sigma, really. Okay, so what we need to do is to produce that pattern. Now remember, both of these p orbitals have the same energy, and both of the sp orbitals have the same energy. So I'm looking for 2 boxes like that, and I want, well, my p's will be a little bit higher in this one. That's the only one that works. If you know your hybridization, it's not too bad, but you do have to work a little bit for it. Okay, last one on this page, group, notebook page, whatever. Which of the following molecules contains only sigma bonds? It's a little bit of work, but basically we're just looking for single bonds. Which ones are all single? So the first one is definitely not. I have a pi bond connecting in here, so get rid of that one. Okay, water. Water is working out nicely for me. And just to be clear, oxygen is that, and nitrogen is that. So sigma bonds, just water. Okay, first half. I'm going to go and sort out the next one, and I will try and get that done as well.